Lecture 10, part 2. Let's continue topic composites. Now you can see diagrams which shows values of Young modulus of elasticity plotted against density for all classes of single materials, metals, organics, natural and synthetic, and ceramics, natural and man-made. We can see namely that if we plot value of Young's modulus against density, then the various classes of materials group themselves neatly into groups when plotted logarithmically. This grouping are shown as the shaded areas in the diagrams, with the contents of each area being marked: engineering ceramics, engineering alloys, like metals and other, etc. This figure shows that all the shaded areas run approximately from the lower left-hand corner to the upper right-hand corner. The top left and lower right corner are largely clear, with no materials marked. Why is this? The blank areas indicate that there are no materials with low or very low density that also have high or very high value of stiffness. Similarly, no dense or very dense materials possess low stiffness value. The latter situation doesn't concern us because high density, heaviness and low stiffness is not a desirable or useful combination of properties. However, materials that combine high stiffness, high Young modulus, with low density, lightness are very useful in transport systems, and especially in the aircraft and automotive industries, where weight saving is of paramount importance. The stability and control of an aircraft in flight depends upon its aerofoil surfaces being presented to the airstream at the correct angle. A large aircraft can weigh up to 500 tons, and the resultant forces on the airframe are very large. If the airframe suffers active elastic distortion because of these forces, then the airfoil surfaces may be presented to the airstream at the wrong angles, and lift and control may be lost. The airframe needs to be light in weight, but it must also possess as high a stiffness as possible. Similarly, with a road vehicle weighing 1 ton and traveling at speed, the wheels and hence the tires must have the correct angle to the road surface to maintain adhesion. The attitude of the wheels to the road depends upon the suspension elements, which are attached to the frame or body shell of the vehicle. In this frame or shell deflects elastically to an excessive extent. Then the wheels will assume unsatisfactory angles to the road surface, and adhesion and control may be lost. The frame or body shell of the vehicle needs to be light and in weight, but must also be as stiff as possible. In construction, glass reinforced polymer composites have been used in the restoration and refurbishment of listed buildings and buildings of great architectural merit. Turrets, finials, and other decorative features, especially those height on the building and visible only from ground level, have been replaced with glass reinforced polymer items made from architect's drawing. They may be completely fabricated in a workshop and then lifted into place and securely attached to the structure. One example was the replacement of a finial to a building in Regent Street in London. Here you can see that engineering alloys, metals, and ceramics have high value of stiffness, but they are also dense, heavy. So despite the fact that we have a high number of materials to choose from, we sometimes cannot obtain the particular combination of properties that we require. Going back to the example mentioned above, we often require a material which is both light in weight and very stiff. Such materials are usually quite dense. So if we need a light and a stiff material, the solution is to take a light material such as a polymer and reinforce it with the fibers of a very stiff and strong material such as glass or carbon fiber. If we make the composite in the correct way, we can obtain a material with a stiffness approaching that of steel with a fraction of steel density. Glass or carbon fiber reinforced plastics are examples of composites. Composites are made because there is no single exciting material that will give us the combination of properties that we require. To restate the definition simply, one material is combined with another in such a way that the resulting composite possesses the required combination of properties. Composite measures in statistics and research design refer to composite measures of variable, that is, measurements based on multiple data items. An example of a composite measures is an IQ test, which gives a single score based on a series of responses to various questions. And three common composite measures include indexes. This is a measure that summarizes and ranks specific observation, usually on the ordinal scale. Scales. This is advanced indexes whose observations are future transformed due to their logical or empirical relationships. And typologies. This is measures that classify observations in terms of their attributes on multiple variables, usually on a nominal scale. Composite survey. Composites include many types. This is a particle reinforced that include large particle and dispersion strengthening. Fiber reinforced polymer or fiber reinforced plastics can be continuous, aligned, or discontinuous, short, that can be aligned and randomly oriented. And also, composites can be structural, laminated or sandwich panels. Here you can see a classification and type of composite material. Many composites are made in order to achieve a particular and desirable set of mechanical or structural properties. This is, however, not the only type of composite. We can make composites for optical, thermal, and electrical reasons too. The manufacturer of cameras and optical instruments make composite lenses from two or more types of glass to achieve lenses free from chromatic dispersion and achromatic doublet, for example. Electrical cable is a composite sheeting and conductors made for reason of insulating electric currents from the structures through which the cables pass or to which the cables are fastened. Similarly, in construction, we use composite blocks to obtain a mixture of compressive strength and thermal insulation. Some purists would argue that metal alloys could be seen as composite materials, but such an argument assumes a familiarity with phase equilibria and the theory of solid hardening, etc., beyond the needs of civil engineers and construction professionals. And in practice, this means confining ourselves to composites made for reasons of strength and thermal insulation. So, composite material can be dispersed, particle reinforced, discontinuous, fiber reinforced, aligned, discontinuous, fiber reinforced, randomly oriented. This is randomly oriented. Continuous, fiber reinforced, aligned. This is discontinuous, fiber reinforced. The next one, continuous, fiber reinforced, aligned, 0, 90 fiber orientation angles. And continuous, fiber reinforced, multidirectional fiber orientation angle. Types of composite: particle reinforced composites, fiber reinforced composites, and structural composites. The first type, particle reinforced composites, used in particle reinforcing ceramics, glasses, small mineral particles, metal particles, aluminium and amorphous materials, polymers and carbon black. And why particles are used? Particles are used to increase the modulus of the matrix, to decrease the permeability of the matrix, to decrease the ductility of the matrix, and also used to produce inexpensive composites. Example: concrete, where the aggregates, sand and gravel, are the particles and cement is the matrix. Particle reinforced composites support higher tensile, compressive and shear stresses. This is an example of particle reinforced composites. The matrix from ferrite, alpha iron, ductile, and particle cementite, brittle. This is spheroidized steels. And this is the next example with matrix rubber compliant and particles carbon stiffer for automobile tire. Fiber reinforced composite. Fiber reinforced composites are made of metals, ceramics, glasses, or polymers that have been turned into graphite, as known as carbon fibers. Fibers increase the modulus of the matrix materials. Strong covalent bonds along the fiber's length gives them a very high modulus in this direction, because to break or extend the fiber, the bonds must also be broken or moved. Uses of fiber-reinforced composites. Sports equipment such as a time trial racing bicycle frame, which consists of carbon fibers in a thermoset polymer matrix, body parts of race cars, and some automobiles are composites made of glass fibers or fiberglass in a thermoset matrix. Fiber orientation in fiber reinforced composites you can see on this scheme. Fiber orientations can be continuous and aligned fiber, discontinuous and aligned fibers, discontinuous and randomly oriented fibers. Structural composites. The properties of structural composites depend on constituents and geometrical design. Structural composites. You can see here staked and bonded fiber reinforced sheets. Staking sequence 0.90 and benefit balanced in plane stiffness. And sandwich panels with low density honeycomb core and benefit small weight, large bend stiffness, face sheet construction, face sheet, adhesive layer, honeycomb, and this is a fabricated sandwich panel. So, structural composites are engineered products made from plastic, wood, glass, or carbon fiber materials. The formed or extruded products have applications as outdoor deck floors, railing, fences, landscape timbers, cladding, seating, molding, trim, and window or door frames. Theory of composites. First, strengths, properties. There are a number of requirements that must be satisfied if we are to successfully reinforce one material with another. These are: the reinforcement must be stiffer than the matrix material. The reinforcement must have a significantly higher value of Young's modulus than the matrix. The reinforcement must be stronger than the matrix material. The reinforcement needs a significantly higher tensile strength than the matrix material. The reinforcement must be properly bonded to the matrix. If there is no bond, we obtain no reinforcement effect.